So in this video we're going to look at the case where we have the tangent being raised to an even power, but where we have no secant factors showing up in the integral. So this particular example, we have the tangent to the fourth power of x dx, and it's definitely meeting the criteria that there are no secant factors and the power of the tangent is even and positive. So the idea is we're going to rewrite this so that we can take a tangent squared factor and convert it into a secant squared minus 1 using the Pythagorean identity. And then we have to distribute and then repeat the process as necessary. So this can turn out to be an iterative process, especially depending on how large this exponent is. So we have the integral of the tangent to the fourth power of x dx. And what we want to do is look at the tangent to the fourth as being the product of two tangent squareds. So we have tangent squared x times tangent squared x is the same as the tangent to the fourth. And this is a dx. And then what we want to do is take one of the two tangent terms that we have and replace it using the Pythagorean identity. So we know from previous videos that 1 plus the tangent squared of x is equal to the secant squared of x. So if we subtract 1 from both sides, we see that the tangent squared can be replaced with the secant squared minus 1. So we go ahead and make that substitution right here. So replace tangent squared with secant squared of x minus 1, still times the tangent squared of x, and it's still dx. And then we distribute this tangent function into the parentheses. And when we do that, right away we wind up with one term that can be easily integrated and one that cannot. So we have secant squared of x times tangent squared of x, which is easy to integrate. And then we have minus the tangent squared of x. And this should all be in parentheses dx. And the idea is this one here is easy to integrate. This is just going to be 1/3 times the tangent cubed of x. So let's think about why that is. If we take the derivative of this, the 3 is going to come down. So we'll get 1/3 times 3 is 1. We'll need to decrease the exponent by 1, so tangent cubed will become tangent squared. And then the chain rule says that we have to take the derivative of the inner function, which is the tangent of x. And the derivative of the tangent is the secant. The other way you could get at this integral, if you didn't want to think about it this way, would be to do a u sub. It's set up so that a u sub works. If we were to let u equal the tangent of x, then du dx would just equal the secant squared, because the derivative of the tangent is the secant squared, which means that du is equal to the secant squared dx. So we could make the substitution. U equals tangent, so we'd have u squared here, and then the secant squared right here, the secant squared dx would get replaced with du. So we would just be integrating u squared. The antiderivative of u squared would be 1/3 u cubed, and then we would replace the u with the tangent function to get 1/3 tangent cubed of x. This one doesn't integrate so easily, so I'm gonna still need to integrate this one, so it's going to be minus the integral of the tangent squared of x dx. And then what we need to do to integrate this is use the Pythagorean identity again. And that's why I said this can turn out to be an iterative process. Depending on the power that we have here, we could need to do this repeatedly. So I'm going to get 1/3. And I probably should put my plus a constant of integration here, because I have done an integration which does introduce that constant of integration into the process. So we have 1/3 tangent cubed of x minus the antiderivative. The tangent squared can be replaced with the secant squared of x minus 1 from the Pythagorean identity from trigonometry, plus our constant of integration. And now we have two terms that are both easy to integrate. We get 1/3 times our tangent cubed, pulling down to the next line, minus parentheses, the antiderivative of the secant squared is the tangent function, because the derivative of the tangent, like we saw here, is the secant squared. And then the antiderivative of 1 is just going to be x plus our constant of integration. And if we desire, we can distribute that minus sign into the parentheses, so that would give us a 1/3 tangent cubed of x minus a tangent of x plus an x plus our constant of integration.